So now we've got our stress diagram, we want to try and work out what the moment diagram is. And the moment is the force. This is the equation for the force. Times the distance from the pivot, we know that. Or from the support. Okay, the moment of this. So as we think about the beam, going back to the original beam here, the moment at any given point, here for example, will be the sum of the force over the distance. So if I've got a UDL, actually I've got to take into account each bit of force as we go along. So it's not a case of, say, just working out what the moment is in the middle. That gives us an idea. But this part of the force is only this small distance away from the pivot, whereas over here, that part of the UDL is actually further away from the pivot. So the effect of that force is increasing. So what we need is to actually sum all those different parts and their distances, which is where integration comes in. So what we do is we say that the actual small change in moment, delta M, is the force, the strain, the stress rather, times by delta R, where R is the distance, delta R. And the moment, the overall moment, is the integral of the force with respect to R, or X if that's our distance. Actually we're using X instead of R, aren't we? So delta X would probably be better in this example, because we're using X to represent the distance. So if I want to know what is the moment between 0 and 2, the first part of our stress curve here, between 0 and 2 meters, I want to integrate the force between 0 and 2. And that will tell me the area underneath the curve between 0 and 2. And last year we physically measured that area. You can do it. It's just a rectangle and a triangle. I can divide it into triangle and rectangle, add up those separate areas, and I'll get the change in moment. And that will tell me what the moment is at this point. And then we put that in. And then, well, how did that moment change? It was a curve. So we put a curve in, if you remember back to last year. But it was sketched. Now we're actually going to come up with the function by integrating between the force function, which we now know, between 0 and 2. So what is the force function between 0 and 2? It's that, minus 10x plus 42.5. So, from A to B, the change in moment between A and B is the integral between 0 and 2 of minus 10x plus 42.5 with respect to x. So this is quite an easy integral to do. Looking at a table of standard integrals, for a function like this, we just add 1 to the power and divide by the new power. And for a constant, the variable x just reappears when we integrate, doesn't it? So delta M equals minus 10x squared over 2, add 1 to the power and divide by the new power, plus 42.5x. And it's a definite integral between 0 and 2, so put square brackets in and put the limits on. And that will give us a change in moments between 0 and 2. We can simplify a bit because minus 10 over 2 is minus 5. So therefore, delta M equals minus 5 x squared plus 42.5 between 0 and 2. And delta M equals, putting in the limits, minus 5 times 2 squared plus 42.5 times 2 minus 0. So that will actually be 0 because when x is 0, the rest of it is 0, isn't it? And so delta m equals 62.5 kilonewton meters, which is what we measure the moment in newton meters, or kilonewton meters in this case. Sorry, slight arithmetic error there. Not my fault, it was them, not others. 65 kilonewton meters. I could start now to sketch my moment curve plot. I know that if this is this is support A, or this is the beginning of the beam and this is the end of the beam, it's going to, actually won't be a support there, so I know the moment is going to start at 0 and end at 0. And so we now know between 0 and 2 meters, so if this was the 2 meter mark, it's starting at 0 and ending up at 65. So I could go up to 62.5 along here, and that's where it's going to. And last year we would have then said, well, what's happening to that moment? The change in moment, it's some sort of curve, so we put the curve on it. What we're going to do now is to actually come up with the function. So we've got a similar problem to what we had before. The function is this, minus 5x squared plus 42.5. So to sketch the function, to sketch the moment change, or delta m, between, for A and B, we have y equals minus 5x squared plus 42.5x plus c. Because if I integrate, I get that constant of integration. Again, we're after where does it cut the y-axis. Because if I plot the curve y equals minus 5x squared plus 42.5x, I'll get a curve which could be anywhere. What locks it in position is this point here where it cuts the y-axis. If I were to sketch this, it's going to probably look something like this. But if I plot minus 5x squared plus 42.5, it can have this shape, but it could be anywhere on this curve. What locks it in position is, where does it cut the y-axis? You know, at what point does it cut the y-axis? Well, in this first one, it cuts at 0. So I know that c equals 0 in the first one. So at A, the moment is 0. Therefore, c equals 0 for A. But later on it won't be. So y equals, so from A to B, the moment curve is minus 5x squared plus 42.5x. So I can now plot that on autograph. So I could start a new page and put that in between 0 and 2. I'll finish this now, and we'll look at it next time, and we'll finish this off. But just to give you a clue, if you've got now a couple of weeks, you could have a go at trying to do this for yourself. We've now got a similar situation as we've had before. If we look at the overall curve, say for this part of the curve between C and D, I now know the equation of that line, and I've got to integrate that. Between C and D, it's this. Whoops. Here. So to get the delta m between those 2 points, I'd integrate it. And now to find the constant c, I would need 2 points. I'd need to know what the moment was when x equals 5, for example. It's going to take a little bit of thought, because of course when I integrate, let's go back to this one we've just done, when I integrated this, I'm going the wrong way. I've done it. When I integrate, I knew that the moment started at 0. So delta m started at 0 and went to 2, and I could find out what is, when I plotted it on the diagram, it started at 0 and went up to 65. The next one is going to start at 65, and then if I integrate, I'm going to find delta m, whatever that is, will be the change in moment between B and C. So I've got to start at 65 and then add or subtract, depending on the value that I get, the delta m to get the next point, and so on. And that will then give you a fixed point in space, which you can then say, ah, right, I now know the moment at that point, so I've got an x and a y, so I can calculate c. So there's a little bit of faffing around to do. My working out is on that piece of paper if you can follow it. So have a go. But after half term we'll get together and we'll check you're okay with that. Okay? So I'll stop there.